Assalamu alaikum. My name is Yacine Khaldi, a PhD student at the University of Buera. I'm pleased to present to you our research entitled Region of Interest Synthesis using Image-to-Image Translation for Ear Recognition. Firstly, we're going to look at biometrics in general and ear biometrics in particular. Secondly, we will move on to the issues, motivation, and objective. Then I present the proposed approach in detail, before proceeding to experimental analysis and finally drawing conclusions. Biometrics are physical or behavioral human characteristics that can be used to digitally identify a person to grant access to systems, devices, or data. Examples of these biometric identifiers are fingerprints, facial patterns, voice, or typing cadence. Each of these identifiers is considered unique to the individual, and they may be used in combination to ensure greater accuracy of identification. So, why do we must have ear biometric? Unlike the face, the ear is regarded as one of the most stable anatomical human features. Also, there is no need to make any physical movement such as moving finger or face. In addition, it is easier to implement continuous authentication. Even if the subject is moving and working, the system works from everywhere. As opposed to the fingerprint or the iris, ear image does not need special equipment to capture. Now, I'd like to focus on the motivations for this research. A typical ear recognition system has this scheme. The ear is detected and cropped out of an input, image, or video source. Then the image is subjected to some pre-processing operations like histogram equalization, illumination normalization, or filtering. The next step is to extract ear features to be used in the classification step. I'd like to mention some problems here. The image of the ear is not without its many flaws, such as hair occlusions, cloth, background, in other words, all non-ear pixels. So feeding this image as it is to the identification or verification system can cause performance degradation. The solution we adopt or we propose here is to use a generative model to generate a synthetic region of interest of the ear that is free of all non-ear pixels. In our proposed ear recognition scheme, we used a tight region of interest synthetic segmentation of the ear instead of a simple cropped image. The region of interest segmentation is synthesized using image-to-image translation, and it is free of all irrelevant pixels. Furthermore, missing parts of the ear due to occlusion or distortion can also be synthesized. This diagram illustrates the proposed scheme. The first step is to scale all images between -1 and 1. Then we synthesize the region of interest of each image using a trained pix-to-pix GAN. Next, we separate the image's color components and divide them into non-overlapping blocks as needed and extract local features. Finally, we concatenate the histograms before feeding them to the classifier. Okay, so let's start looking at the generative model. It is a deep conditional generative adversarial network, or GAN. Before the generator can be used on its own, it must be trained in parallel against the discriminator. Moving on now to the architecture of the generator model. It is a deep unit model that has a symmetric structure with 8 encoding layers followed by 8 decoding layers as illustrated in this figure. On the other hand, the discriminator takes 2 images, an input image and an unknown image, and tries to decide whether the generator created the unknown image or not. Its architecture is straighter than that of the generator. It is composed of 5 convolutional layers. The average of the output layer is the probability that the image is real or fake. For the segmentation synthesis process, the first performance metric we choose to measure is the pixel-wise color accuracy. It is defined as the ratio between the number of pixels that are correctly colored to the total number of pixels. The second metric we used is the intersection over union. It is the overlap between the predicted segmentation and the ground truth divided by the area of union between the predicted segmentation and the ground truth. On the other hand, we used the rank 1 recognition rate to assess the performance of the classification model. We trained the pix-to-pix GAN using the region of interest dataset created from the well-known annotated web ears dataset for 32,000 iterations. This figure shows the convergence of the loss for both the generator and the discriminator over training epochs. Examples of region of interest segmentation images generated by the GAN are shown here. We can see some distortion on the edges. We believe that training the generative model using a combination of ear datasets leads to a better performance, as the model will be able to recognize more ear shapes with different poses, variations, and scales. Although, this requires preparing a large ground truth region of interest dataset. The intersection over union values of the generated region of interest segmentations were between 86 and 97%, with an average of 94%, as shown in this table. The pixel-wise accuracy varies from 43 up to 97%, with an average of 83%. The histogram of intersection over union and the pixel-wise accuracy distributions are shown in this figure. Most intersection over union values are centered on 94%, whereas the pixel-wise accuracy values distribution was wider than of the intersection over union. The second half of the experiment is feature extraction and classification, where we used LPQ and BCF descriptors to extract ear features and feed the histograms to a nearest neighbor classifier. The same experiments with the same set of trained test images are carried out using both the region of interest and the original annotated web ears dataset to focus attention on the benefits of region of interest synthetic segmentation. In all three scenarios, synthetic ear region of interest images yielded a higher rank 1 recognition rate, as shown here. To summarize the main points of this presentation, we tried to bridge the lack of research on the topic of ear region of interest synthetic segmentation in literature. We proposed to employ image-to-image translation not only to synthesize the segmentation of the ear, but also to patch missing parts and discard occlusions as possible. Furthermore, it is possible to generate ear region of interest segmentations with uniform rotations and sizes. Thank you for listening, and I'll be happy to answer your questions.